Hello, Panther! Today I will show you an informal derivation of so-called Itô's lemma. Itô's lemma or Itô's lemma is very important in so-called Itô calculus, Itô's calculus, and also in a Fock-Planck equation could be used as that, and all kinds of stochastic motions are solved by this lemma for differentials of random processes. Okay, so first let us begin discussion of what a process is. For example, a random walk can be a process. It's some evolving process, evolving event in T. If it's stochastic, it can be describable using some function x dependent on T. There is a graph of such processes. They start at some value and then they move up and down like shares on the stock market, yes. And this x of t is process. It's not function. It's something new because it's not unique. Yes, it can be this function. It can be this function. It's a random process, a random function. Random walk is a stochastic process with initial position 0. Okay, Markov process is such process which doesn't depend on the previous position started. So that means that if a price, for example, of some stock is high, then it can either the price can be higher or lower, but it's not depending on the actual price. For example, martingale process is such that the expected value of the next step for any expected value of next step is when we are at some position x, is at some position x, so that means it's not drifting. This process is not drifting, so if we are on some price, so that means that we are not going up and down in next. There's no favor in either direction. Okay. What is Wiener process? Wiener process is one specific martingale process. It's even Markov process because it doesn't depend on position, which is like that, which has these properties, defining properties. V at 0 is 0, so it's a random walk. Expected value of this W at some t is 0, so no matter where we are, the expected value that we are at some t is 0. So it means that you can most probable are positions where the particle hasn't moved or the particle is back when it started, yes, or something like that. What is expected value of square? Because this is 0, this previous one, so it means this is variance. Variance, it's t. It's defined as t. This is classical Wiener process, and that means that the part when time progresses, that means that the particle can be more far away. Okay, so it's very like not so disturbing that this can be like this. What is distribution of what is a distribution? It's normal, yes, and it may be, yes, it's normal distribution assumed, but okay. And for a differential of w, that means that the difference between one point at the process and the other point in next time squared, it's also dt, okay. This is the differential like with respect to time, yes, the next part, next step and the previous step, and this should be also dt, multiple of that differential, okay. Now let us move on and define what is called Itô's process, yes, Itô's process, and this process is more general but not so different from the previous one. In this process, the expected value of differential of this process, it's not zero, but it can be some mean. Yes, it can have some drift, and here the drift is proportional to dt, differential of time, and the constant of proportionality is mu. It's going to be mu, and mu can be a function of t and also x position where we are currently at the stage of evolution. The variance of differential can be also anything, yes. Variance could be anything, so variance of differential is also can be some function of sigma squared, and also it's let us write it as proportional to dt. For Wiener process, sigma was 1. This is just some multiple. It can be a function also of t and x of t. Okay, and we can write it this Itô's process as this. Itô's process, the differential of Itô's process is here in green box. This is differential of Itô's process. I can move it a bit lower. Okay, this is differential of Itô's process. Mu dt plus sigma dwt, where dwt is differential of Wiener process. How does one prove? One can write differential of Itô's process like this. So it's it means why can one write that it's sum of some differential of t plus Wiener process? Well, one has to prove that this differential satisfies all the properties of Itô's process. The first one, there is a proof. The first one is that expected value of this differential should be mu times dt. Well, if you substitute in, you get the sum of these two, but this expected value is computed for some given time, constant time, yes. So that means that sigma as some function is can be held constant or moreover constant, yes. And what matters are these differentials. So expected value of this differential dv, this is 0 from the definition of Wiener process, and expected value of constant is constant. So this will result in mu dt. So the first property is satisfied. Expected value of difference of this squared is then, because dx, this is dx with line, and this means expected value substituted from here. So this is this mu dt plus sigma dv minus mu dt, that's sigma squared dv squared, and this is d sigma squared dt, because expected value of square of differential of Wiener process at some t is dt. Okay, So this can be written as this. Or another type or another way to write it is to integrate it formally integrate it to get that xt is equal to some current some zeroth position plus integral of this with respect to t plus stochastic integral, which is what this can be. This is very interesting part. This is expected part, and this is another more interesting part for me. Stochastic part, stochastic integral. I will define it later, but it can be defined with this differentials. Okay. For expected value, integral and is interchangeable. This is time integral. But okay, let's move on to Itô's lemma. Okay. Itô's lemma. If x is some Itô's process, so that means that it can be written as this, then we can construct another random process of like this. For any time, you just write some function g of xt. So first you compute the x, compute x as a process, and then you substitute in this function, and you will look to the graphs. How do they look like? And very interestingly, they have very similar form. They form another process, which is itself Itô's process, because it can be written as some multiple of differential dt plus multiple of differential of the process is differential, and these are the coefficients: partial derivative with respect to t plus partial derivative with respect to x times function mu plus this half and sigma squared dt, and this partial derivative with respect to x sigma. It's very interesting. Oh, this is some nonsense over there, sorry. This is the correct formula. This is for some mu is 0. Yes, this is expression for mu is 0. But generally this is true for any mu functions. Well, what is the proof? First, write the differential as a function. That means that it's very informal proof indeed. Differential g is equal to g with respect to t times dt plus g with respect to x times dx. But I will add another terms in Taylor series as this 1/2 g double x dx squared plus g xt dx dt plus 1/2 g double t derivative dt squared plus ... Okay, this is true. Then I will substitute in differential of dx as a process, because indeed x was a process, so let us substitute in this, and you get the differential of g looks like this. Well, what are the properties of this differential? I will show that this is indeed also Itô's process. What is the proof of that? I can't tell you, because it may be rather formal, but let us assume it's true, because it's just some scaling, because for some very small amount this is just summing and multiplying, and it will not change the basic core of the process. So it may be Itô's process. Let us guess Itô's process. So what are the new function and new sigma function for this process? Well, let us first look for expected value of this differential g, and you will get this is constant, so this will give you this. And what is this equal to? This is constant, but this is sigma gx times dv, but dv, expected value of dv is 0, so this is 0. And what are next non-zero terms? The only non-zero term, this term is proportional to dt squared, so I won't include this term, and this term is 0, but this term, because expected value of dv squared is this is differential squared, but its expected value is dt to the first power, so that means I have to include this term. The other terms will be higher order, so I will cut this Maclaurin series at here. Well, so these are the terms, and then you have to find expected value of dg minus dg expected. So that means that you have to find dg minus dg with bar squared. And if you do that, these terms will subtract, and these terms will subtract. All terms will subtract, all terms except this, but this squared is differential squared. This is to the power of many, yes, this is power of 4, and there's 2 powers, so this is not going to be added. So the only term which remains is this, gx sigma dv. So that means that expected value is exactly this, so it's gx sigma dv. And there should be something like absolute value of g with respect to x, because otherwise it's not positive. Yes, I have forgot that sigma should be positive, so that means that there should be absolute value to this g. But when g is increasing, that no problem with this, because but never mind, if this was negative, this process is up and down, so I think negative values don't matter, so it can be negative or positive, so no problem with this, so it can be as like this, because what is more important is that what is variance, and variance is the same whether sigma is positive or negative, because squaring will make everything positive. So no, I think it can be like this, no problem, no square rooting. Okay, so this was the Itô's lemma, and we can use it later, and I will use it extensively in my next discussion on stochastic calculus and some differential equations, Itô's calculus, and hopefully I will derive some equations and I will solve them like Black-Scholes equation or Fock-Planck equation, I don't know. But there are plenty of equations from Itô's calculus. Okay, so I hope you enjoyed that video, and maybe next time.